So as we begin Chapter 7, we're going to start looking at gravitation. So we're going to start paying attention to the path of planets and how they orbit around each other, the gravitational pulls that hold those planets in their particular orbit, and we're also going to be able to look at the gravitational force between two objects following Newton's universal law of gravitation. Okay, so we're going to start first with something called Keplers Laws. And Keplers laws have to do with the period and the radius or the distance between planets. And we look at Kepler's laws of planetary motion. So we're looking at specifically these planets and how they orbit, what their orbits look like, what their shape is, how fast they're traveling in their particular orbit. Okay, so this law of planetary motion, or these three laws actually, they give us this detailed description of the motion of our planets. So Kepler has three laws. The first law says the path of each planet about or around the sun is an ellipse with the sun at one focus. And what we mean when we say focus is that there's a focus point within this particular planetary orbit, and the sun is at one of those focus points. So here's a diagram of what this particular law looks like. Our planet here is in an elliptical pattern, which means kind of a stretched out circle. The sun is located at one of these two focus points. Okay, so no matter where it is in its orbit, the sun is always located at one of these two particular focus points in the elliptical. Moving on to Kepler's second law. Kepler's second law tells us that every planet moves so that it covers the same amount of area over an equal period of time. Okay, so an imaginary line drawn from the sun to the planet sweeps out equal areas and equal periods of time. So here you can see if my planet was moving from point A to point B in this amount of time, it might cover this certain amount of area. Okay, drawing our lines directly to the sun. And we remember that the sun is at one of those two focus points we saw in Kepler's first diagram. Okay, and here it is, it's located at one of those two focus points. However, if our planet moves from point A to point B in this certain amount of time, which happens to be a smaller amount of time, it also covers the same amount of area. So these two triangles here, although they look different, actually covers the same amount of area. Okay, and here, where we cover a lot of time, we still cover that same amount of area. Okay, so that has to do with this being an elliptical path rather than a circular path that this math works out. Okay, so that's Kepler's second law. So now we'll move on to Kepler's third law, which has the equation that goes with it. Okay, Kepler's third law has an equation that goes with it. And let me just talk through the law here a little bit and you can write down that equation. So the third law says the ratio of squares of any period of any two planets revolving around the sun is equal to the ratio of the cube of their distances from the sun. Okay, so T is the period for any two planets. Remember, T, or period, is time it takes for one revolution. Okay, T is the time it takes for one revolution, and we want T, or period, always to be in seconds. Okay, so T is the time it takes for any object to make one complete revolution. So here in this case, T would mean the time that it takes for planet A to revolve around the sun one time. Okay, so T sub A would mean that's the time required for this planet A to orbit the sun one time. TB would be the time for planet B. So here we're comparing these orbits of two different planets. Okay, R is their radius or their distance from the sun. So when we look at R, we're talking about the radius, but really we're looking at distance from the sun. And we want that radius value to be in meters. not kilometers, not centimeters. We want it to be in meters. So you might have to do some conversions there when you look at the distance between these two objects. Okay, it must be in meters. So period, which is capital T, should always be in seconds. Radius, which is always in meters. When we're looking at these equations, we can rearrange the equation to give us a look to evaluate basically one planet or another. Okay, so here all we're doing is rearranging this equation, doing some algebra to rearrange, where we have all of planet A on one side and all of planet B on another side. Okay, these two equations are equal to each other. Okay, they mean the same thing, they help us solve for the same thing, but we can rearrange them to look at all of planet A's characteristics should be equal to all of planet B's characteristics. So when we look at this value, r cubed over t squared, this should be the same value for every single planet, because we see that we can set planet A and planet B equal to each other based on their radius cubed over their period squared. Okay, so for every planet, r cubed over t squared should be the same value. So let's go ahead and try a practice problem here. Go ahead and pause the video and get written down what you need to, but our overall goal here is going to be to determine the distance from Mars to the Sun using Earth as our reference point. So our goal is going to be to determine the distance from Mars to the Sun. So we want to find radius between Mars and Sun. Okay, so we're solving for r sub ms. This distance right here, r sub es, is equal to the radius or the distance between the Earth and the Sun. T sub m would be the period of Mars, and T sub e would be the period of the Earth. Okay, so the distance that we know between the Sun and the Earth, or the Earth and the Sun, which is listed as one of our variables right here, is equal to 1.5 times 10 to the 11th meters. Okay, so that's one of our values. It tells us right up here that the period of Mars, T sub m, is equal to 1.88 years. Okay, usually we want our period to be in seconds. When we're comparing values like this, as long as both of the periods are in the same unit, you can keep them in years or months or days or whatever. But for most problems, we would like t to be in seconds. However, we're going to go ahead and leave the period of Mars here in years. That means the period of the Earth needs to be in years as well. Okay, so t of the Earth we know is equal to 1 year. Okay, the Earth completes one orbit around the Sun in 1 year. So that means t of the Earth, or period of the Earth, is equal to 1 year. If we needed it in days, we would keep it at 365 days. If we wanted it in months, we'd know 12 months, all that kind of stuff. But if we wanted it in years to match the period given to us for Mars, we know that the distance, or the time, it takes the Earth to travel one complete time around the Sun is 1 year. So now we can go ahead and just start plugging in some values. We're going to solve for r sub ms. We're going to solve for radius between Mars and the Sun, or the distance from Mars to the Sun. So we're going to take r sub ms over radius of the Earth, 1.50 times 10 to the 11th. These should both be cubed, right, because we have a cubed value here on the outside of our parentheses. All I'm doing is moving that cubed inside of the parentheses since one of our variables needs to be solved for. Okay. On the other side, I'm going to take the period of Mars over the Sun, and I could just square that whole term since I have both of those terms right there. Okay, so we need calculators out if you don't have those out yet. I want you to go ahead and pause the video and work the math yourself to see if we match answers. If not, I'm going to walk you through the algebra it takes to do this problem. So I got a final answer of 2.28 times 10 to the 11th meters. Okay, so if you got that, that means your algebra looks good and you can skip past this next part where I'm going to walk through the math. If your math did not come out exactly to that, I'm going to walk you through how we did that algebraically. Okay, so algebraically what I want to do here is show you where we're starting from, which is this equation down in the bottom left. Okay, which I moved up to the top. The first thing that we should do is combine this whole term or solve for this whole term since we have every variable there. So we're going to take 1.88 divided by 1 and we'll square that value, okay, which gives us 3.53. And that's equal to r sub ms cubed over 1.50 times 10 to the 11th. That value is cubed as well. Okay, now since we've got this three value system right here, our variable is on top that we want to solve for, so we're going to multiply these two numbers together. I'm going to start by squaring that term. So in my calculator I'm going to punch 1.50 times 10 to the 11th. And I get 1.5 times 10 to the 11th, and I'm going to square that value. So you can square it by either hitting enter and then caret 3, or if you've solved that 1.50 times 10 to the 11th and it's in your calculator, you can hit math and then scroll down to number 3 where it says cubed, and then you should come up with answer cubed on your calculator. Either way, that should give you r sub ms cubed over 3.375 times 10 to the 33rd equals 3.53. From there, I'm going to multiply these two terms together. Okay, so I'm just going to go ahead and hit answer times 3.53. And I'm going to move my equation up here. So by multiplying that across, that leaves me with r sub ms cubed equals 1.19 times 10 to the 34th. And then to get this r sub ms by himself, I need to cubed root both sides. Okay, and to do that in your calculator, you should still have the value 1.19 times 10 to the 34th on your calculator. You're going to hit math, scroll down to number 4, then you can hit second answer and insert that value into your cubed root. If not, you can punch it back in, that's fine. And that should give you a radius value of 2.28 times 10 to the 11th meters. So that's all we're going to do with Kepler's laws. The third law, again, is the only law that has an equation that goes with it. That equation should go on your equation sheet for Chapter 7. We will use that one every so often, so just make sure you have that on there. You can put both versions, the first or the second version, it does not matter. They're the same equation, essentially. They're just set up two different ways. Okay, so either equation can go on there. Now we're going to move on to Newton's law of universal gravitation, or I'll sometimes refer to it as the universal law of gravitation, which is abbreviated U-log. Okay? Universal law of gravitation. Okay, so if you see that acronym somewhere, that's what that means, universal law of gravitation. So Newton started looking at these gravitational models, and he started to wonder, why did the moon keep its circular orbit around the Earth? What was it that kept it in this pattern when Kepler discovered that they were in elliptical patterns? Why does the moon have a circular or very near circular pattern? Okay, so he started to look at the gravitational force between the Earth and the moon as compared to the gravitational force on the surface of the Earth, to see if that had anything to do with why the moon was kept in a circular orbit. Okay, so he started looking at the gravitational force between these two objects. This italicized paragraph here is Newton's law of universal gravitation. So this particular paragraph does need to go in your notes. It's his word-for-word explanation of this universal law of gravitation. Okay, so it says every particle in the universe attracts every other particle with a force that's proportional to the product of their mass and inversely proportional to the square of the distance between them. The force acts along a line joining the two particles. So go ahead and pause the video here and get that whole entire paragraph written down. You will need that in your notes under the universal law of gravitation. So something that I want to point out here is that this last line says this force acts along the line joining the two particles. So what we're talking about here is every single particle in the universe and every single object in the universe has a gravitational force between them. Okay? So gravity is essentially attracting every single object on the earth. So these two people standing next to each other have a gravitational force that's attracting those two people. Is the gravitational force ever enough to make those two people start to randomly slide together? No. Okay, this would never be a gravitational force large enough to start putting these bodies in motion. The reason for that is because the gravitational force between the Earth that we stand on and ourselves is much, much, much stronger because it's proportional to the masses of the objects. So the masses of these two people does not compare to the mass of the Earth and the person. Okay, so those two people would never start sliding together. However, there is a gravitational force between them. When it says this force acts along the line joining the two particles, that means that for some reason, if these two particles would begin attracting and sliding towards each other, they wouldn't slide in a zigzag path. They wouldn't have a gravitational force that goes down to the earth and then back up. The gravitational force between them acts in the shortest possible distance between those two objects. So after looking at the radius of the earth and the radius of the moon, after looking at the gravitational force exerted by the earth on any object, he noticed that as you decrease the distance between those two objects, between the earth and whatever object you're looking at, the gravitational force decreases. Okay, so as something gets farther and farther away from the center of the earth, which is where gravity pulls from, that means the gravitational force decreases as well. Okay, so he also looked at the fact that the gravitational force has to be proportional to both of the masses of the objects. More often than not, we look at the mass of the earth being one of those objects, and the mass of whatever we're looking at, whether it's a person, whether it's the moon, whether it's a ball sitting on the surface of the earth, any object we're looking at to compare the gravitational force of, we're looking at the mass of the object and the mass of the earth. Okay? If we're looking at the mass of two objects sitting next to each other, we would take into account the mass of each of those objects and not really look at the gravitational force that the earth exerts here. So this is the equation that Newton came up with for his universal law of gravitation. And this is a big, big, big equation that we will use very, very often in this chapter. So this does need to go into your equation sheet and into your notes and a star by it and everything like that, because this one you will use a lot. And I'm going to go through what each of these variables mean so that you have a good understanding when we're solving for these problems what we're looking for. Okay? So when we talk about F here, we're really talking about the gravitational force or the force due to gravity. So this F sub g, we've seen before. Okay, we've seen that on the Earth's surface, F sub g is equal to mass times gravity. And what's little g here? It's the acceleration due to gravity, or mass times 9.8. Okay, that's on the surface of the Earth. This equation is for comparing things that may be on the surface of the Earth, they may not be. So that's where it gets a little bit different. But we understand it's the same essential gravitational force that we're looking at here. Okay, so that F is F sub g. It's the gravitational force between two objects, whether it's the Earth and an object or whether it's two objects sitting next to each other. G, big G here, is called the universal gravitational constant. And G has this value, 6.67 times 10 to the negative 11th Newton times meter squared over kilogram squared. This unit means that in order for G to work, our force has to be in newtons, our radius must be in meters, and our masses must be in kilograms. Okay, in order for this constant to work, which we will need this constant every time we use the equation, we know that our force has to be in newtons, our radius has to be in meters, and our masses both must be in kilograms. Okay, this value, again, you'll need to write down. We use this value a lot. Okay, you'll probably have it memorized by the end of the chapter because we plug it in so much into our calculator. 6.67 times 10 to the negative 11th. Make sure you get that negative there. All right, M is the mass of object number 1, M2 is the mass of object number 2. One of these could be the mass of the Earth, if we're looking at the force due to gravity of an object on the Earth. And I'll give you the mass of the Earth here in just a second, but these two masses both must be, again, in kilograms. Okay, and last but not least, I didn't write this down, R is the radius. But it's essential here that you understand this is the distance from the object to the center of the Earth. Okay, so if we're comparing something that's on the Earth or on the Earth's surface, we need to have a distance from the object to the center of the Earth, not to the Earth's surface. So I will give you some numbers here that you can look at here pretty soon with the radius of the Earth and all that kind of stuff. But you need to understand that the R value here is from the object to the center of the Earth. So we're going to go ahead and try one here. So go ahead and pause the video and get this problem written down, and then we're going to work through it. So this tells us a 50-kilogram person and a 75-kilogram person are sitting on a bench so that their centers or their center of mass is 50 centimeters apart. What's the magnitude of the gravitational force each exerts on the other? So the important thing here that this last question asks us, gravitational force each exerts on the other, there's only one gravitational force between the two people. Okay, and it's equal. So whatever gravitational force person number 1 exerts on person number 2, person number 2 would exert that same equal and opposite direction force on the other. So we only have one value here that we're solving for. They each exert that same gravitational force on the other. So what we're going to do here is we're going to start taking down our values. M sub 1, or mass of the first person, is 50 kilograms. M sub 2 is 75 kilograms. Those are both in the correct unit, so no converting. We don't have to do any converting there for our masses. Our radius was given at a value of 50 centimeters. Is that the correct unit that we need? No, it is not. We need it to be in meters. And to convert from centimeters to meters, we're going to move that decimal place 2 to the left and get 0.50 meters. And then we know our G value. We know big G is equal to 6.67 times 10 to the negative 11th. And we're going to solve here for F sub G because it asks us what's the magnitude of the gravitational force. So that means we're solving for F sub G, or just F in our equation. So we're going to use Newton's universal law of gravitation. F equals G m1 times m2 over r squared. It's important for you to realize that these masses should be multiplied by each other, not added together. Okay, so we're solving for F. We're going to plug in G. We'll take 50 times 75 over 0.5 squared. We cannot forget to square that radius value. That's a very, very common algebra mistake that people make in these problems. We cannot forget to square that. Okay, that's very, very important. And just the radius gets squared. Okay, so 0.5 needs to be squared. So go ahead and plug this into your calculator. I kind of work through it usually starting here, and I'll work my way across over to the force. Okay, so I will start by taking 0.5 squared, then hit enter. Then I'll take 50 times 75 divided by second answer. That whole parenthesis term gives me a value of 15,000. I'm going to take that times G. In this chapter, I think it's very, very, very important that you begin to use that EE button for your exponents, because we're going to deal with a lot of values that are in scientific notation. So to avoid as much error as we can, it's easier and more convenient, I think, to use that EE button on your calculator. So that if you use the EE button on your calculator, you would have a value that looks like this in your calculator, 6.67 E negative 11. Okay, 6.67 second EE and negative 11. That button in your calculator tells your calculator you're working in scientific notation rather than hitting times 10 to the caret negative 11. Your calculator does not know you're working in scientific notation there. Okay, so to avoid some errors just in plugging numbers in, I think it's a good idea for you to start working with that E button. Okay, so our force due to gravity comes out at 1.00 times 10 to the negative 6 newtons. Okay, so we're going to go ahead and try another one here. Force of gravity between two masses was 14 newtons when they were 10 meters apart. The distance between them changed, and the force became 56 newtons. How far apart were they then? Okay, so if our force of gravity went from 14 newtons to 56 newtons, what can you probably guess happened to these two objects? Do you think they got farther apart, or do you think they got closer together? Hopefully you've answered here that they've gone closer together. Okay, as our force due to gravity increases, that means our radius must decrease. Okay, our radius must decrease. So we're going to go ahead and start working through this, and even though we don't have the masses, that's okay. I'm going to show you how we can work with this. So our force due to gravity, to begin our problem, F sub g was equal to 14, and our radius was 10. Okay, and we know what g is, so I'm not going to write down what g value is. But we're going to go ahead and plug that in. 14 equals 6.67 times 10 to the negative 11th. M1 times M2 over R squared. Okay, so between these two instances, will the product of our masses change at all? M1 times M2 should be the same for both of these instances, right? The masses of our objects are not changing. The only thing that's changing here is the radius, which then changes the force. So the masses of our objects aren't changing. We don't necessarily care about the individual masses here. We're going to solve for M1 times M2, this whole term, to allow us to then solve for the radius in our second instance. Okay, so to do that, to solve for this M1 times M2 term, I'm going to start by dividing over my 6.67 times 10 to the negative 11th. I'll take 14 divided by 6.67 times 10 to the negative 11th. Again, when you divide by something in scientific notation, you have to be very careful if you're not using the E button. If you are, you don't have to include parentheses. If you are not using the E button, you need to include parentheses around that term. Okay, so your calculator knows. That gives us a value of 2.09 times 10 to the 11th. Equals M1 times M2 over R squared, so 10 squared. Okay, and we know that 10 squared is equal to 100, so I'm going to go ahead and just plug in 100 down here. I'm solving for this term as a whole, this M1 times M2 term as a whole, because I know between the first and the second situations here, my masses are not changing. So to solve for M1 times M2, that term, I'm going to multiply these two numbers together. So I'm going to take that 2.09 times 100, and that gives me 2.09 times 10 to the 13th equals M1 times M2. Okay, and I don't need to break that down anymore into individual masses. I can leave it at that. Okay, but that's not what my question's asking me for. It's asking me for how far apart were they in the second instance. So now I'm going to take this M1 times M2 value, and I'm going to be able to plug it in our next instance, our next situation, to solve for the radius. So in our second situation, I know that the force due to gravity is equal to 56 newtons. I know that my M1 times M2 equals 2.09 times 10 to the 13th. And I'm going to solve this time for R. I'm going to solve for R this time. So, again, first algebraic thing I'm going to do is divide by 6.67 times 10 to the negative 11th. So I'll take 56 divided by 6.67 times 10 to the negative 11th. And I'll have to move my equation over here. That gives me 8.4 times 10 to the 11th equals 2.09 times 10 to the 13th over R squared. Okay. So when we have a situation or an algebra term that looks like this, my step is going to be to switch those two places. Remember that? If I've got my variable on the bottom, I'm going to switch those two places. So that's going to leave me with R squared equals 2.09 times 10 to the 13th divided by 8.4 times 10 to the 11th. So I'm going to do that math. 2.09 times 10 to the 13th divided by 8.4 times 10 to the 11th. Okay, and that gives me an R squared value of 24.88. So to get R by itself, I'm going to take the square root of both sides. And that gives me an R value of 5 meters. Okay, so that means our radius went from being 10 meters apart to 5 meters apart. These things went from 10 meters apart to 5 meters apart. Our force, however, more than doubled. It quadrupled. Okay, so even though our distance between our two objects was cut in half, our force did not just simply double, and that has to do with our radius being squared. Okay, R squared has to do with that. All right, we're going to try one last problem here, and we're looking here at a spacecraft or something orbiting two Earth's radii from the Earth's center. And let me kind of explain what that means in a picture first. So here's our Earth. The radius of the Earth goes from the center to the Earth's surface. Okay? So when it says it's orbiting at a distance of 2 Earth's radius from the center, that means it's orbiting one radius from the center to the surface, and it's orbiting another distance that just so happens to be equal to the Earth's radius. So that means the satellite is in orbit about that distance from the Earth's center. Okay, so it just so happens to be at a distance above the Earth's surface that's equal to the distance from the surface to the center of the Earth. Okay, and this radius of the Earth value is very important, and we use it a lot. So radius of the Earth has a value of 6.38 times 10 to the 6 meters. That's a number that I will always give you, but should probably go on your equation sheet and definitely in your notes so that you have it handy. You use this value a lot. The mass of the Earth I'm also going to give you, since we're going to use that a lot and we're going to need it in this equation. The mass of the Earth is 5.98 times 10 to the 24th kilograms. Also one that you will use a lot, so should go on your equation sheet. But now we're going to go ahead and start solving here. So we need to solve for the force of gravity, or F sub g. So let's go ahead and set up our equation here. F sub g is equal to 6.67 times 10 to the negative 11th times m1, which is, we'll just say, the mass of the Earth, and m2 is the mass of this spacecraft, which is 2,000 kilograms, over the radius. And when we're talking about the radius, we want to know exactly how far this object is from the Earth's center. Okay, so radius of the Earth is 6.38 times 10 to the 6th, but our spacecraft is orbiting at a distance of 2 radius of the Earth. So that means since it's orbiting at a distance of 6.38 times 10 to the 6 meters above the surface of the Earth, and we want our radius to be from the object to the center, we need to add those two values together. Okay, so we're going to take 6.38 times 10 to the 6th plus 6.38 times 10 to the 6th, and we square that whole entire term. Okay, you could have also taken 6.38 times 10 to the 6th and multiplied it by 2 since it's 2 RE. But you can also just add those together. The reason we're doing that, and this is important, is because radius should always be from the center of the Earth to the object. Okay, so here, if our object would have been sitting on the surface of the Earth and not orbiting at a certain distance above, we could have just used 6.38 times 10 to the 6th. Since it was orbiting at a certain distance above the Earth's surface, we have to add those two together. That's very, very, very important. Okay? So now we can just go ahead and start doing our math. So if you want to go ahead and try and plug this into your calculator, right now just hit pause, and then you can see if we match answers here in just a second. So for my force due to gravity, I got a value of 4899.5 or 4,900 newtons. Okay, and so if you didn't get that, I'm going to show you how algebraically we go about doing that. If you did get that, then that is it for this video, so you can go ahead and start on your homework. But if you didn't get that, I want to show you how we can go about solving for this. Okay, so my first step here is going to be, I usually start on the bottom. I usually start with this term right down here, the radius. Okay, so in my calculator, I'm going to hit 6.38 times 10, or E. I use the E button. E6 plus 6.38 E6. And then I'm just going to hit square, and it's going to square my entire answer. So when I added those two together, I got 1.276 times 10 to the 7th. I'm just going to go ahead and hit square on my calculator, and it's going to say answer squared. And I'm going to hit enter. Okay, that gives me a value of 1.63 times 10 to the 14th. Okay, so then I'm going to move to the top of my fraction here. I'm going to say 5.98 times 10 to the 24th times 2,000 gives me 1.196 times 10 to the 28th. And I'm going to go ahead and divide those. So I'm going to just hit divided by, and it's going to take that answer in my calculator divided by 1.63 times E, or second E, 14. Okay, that gives me a value of 7.34 times 10 to the 13th. Okay, so that's that whole term right there is 7.4 times 10 to the 13th. After that, I'm going to multiply it by my G times 6.67 times 10 to the negative 11th, and I get a value of 4894.06, a little bit differently this time, just a rounding thing, but we're somewhere around 4,900 newtons, which is what we want. Okay? And that is it. That's where we're going to stop with notes for today.